Good. And so we're on. Mic, check, check. Check, check, mic, check. Let's do it. All right, so today we're talking about the physical geography of North America, focusing in on landforms, how they came to be, and then we'll take our halftime break and then talk about the climate. And so first off, we've got to have to conceptualize things. So once again, I talked about how we haven't really mentioned the whole human thing. We're not going to touch on humans at all till maybe the end. We might sprinkle a little bit in there. So all we're going to focus in on is everything that happened on North America leading up to the arrival of human beings. And to kind of give you a perspective, how old is Earth? So you can do this for your future educators, a simple thing to do, to show your students how old Earth is. Just essentially stick your arms out in both directions, so you have essentially your arms horizontal. So you want to be horizontal, so I'm stretching out as far as I can. Ladies, I know a few of you might have a nail file on you. So if I essentially got out my nail file and I got on my middle finger here, so my middle finger and a little bit of the dust that fell to the ground. This is how old Earth is. The amount of time humans have been on that Earth is the dust that fell from the nail file on my little fingernails. So that kind of shows you how long the Earth has been evolving, creating the physical structures that then just now recently here humans have been occupying. And so we're going to come back to, at the end of this discussion, it talks about, they've been beaten up, I've been reading all the North American geography books, they've been beating us up saying we are the most human changed continent in the world. No other continent has been changed as much by humans as this North American continent. And a lot of that's kind of relating it to current things, agriculture. But one of the things we'll talk about at the end of today's lecture, there's this whole myth that that Christopher Columbus came upon a pristine, untapped, untouched civilization, untouched physical geography. That's not the case. The Native Americans no doubt left their impact as well. A story that's never told. And so just to kind of give us an idea of how stinking long the Earth has been around compared to humans, we are just a little speck of dust that falls to the ground. And so what we're going to attempt to do here is cut a slice right down the middle of North America here. And so we're going to slice right down the middle here. And so what I'm going to do is just like how we slice down the middle of a pie. Slice down the middle, we're going to remove half of it, and now we're going to take the half, and now we're going to look at it from the side view, so the cross-section view. So essentially we're going to kind of go through North America, looking at its changes. Very, very simple here. And so let's do it going from west to east. So this is another thing I included in I'll include on course. Unfortunately, this morning at 4 a.m. when I woke up to do this lecture and design this lecture, I got really into the black stuff. Cool, black. But then, of course, printing it out is a disaster. So I, of course, need to fix this to make this obviously more printer friendly. So give me a weekend, give me maybe a couple weekends to figure that out. But nonetheless, I think we can follow along, and I know we can all draw. And so let's see, what am I trying to show here? And so over here, the west coast, over there, the east coast. And for the most part, we all know that, I hope by now. And so here is the profile. So once again, if I slice right down through North America, and then I now look at the side view, after removing half the pie, this is what I would see. Something along the lines of this. And so I would see two jagged edges, a kind of a bowl here, but a bunch of jagged edges there. Boom, our highest elevation change, and then a very flat, and then another elevation change, and then we got, of course, our good friend the Pacific Ocean here is the teal, and our good friend the Atlantic Ocean there. And so let's go through each of these. And so in the map quiz, you would have had to know where the coast ranges are. And those are the coast ranges in California, or the coast ranges there in British Columbia, there in Canada. And so either way, both of those have this characteristic along the Pacific Ocean, a mountain chain. One of the things you'll also note is from mountain down, it's a very quick descent. And so there, the beaches, if you look over on the Atlantic side, very, very flat, the change from surface area to underwater. Very, very gradual change. Here, very, very, very steep. So we look at one of the steepest parts as far as the Pacific Ocean is actually here along the North American coast. And we'll come back to explain that. What's this red dashed line right through here? Anyone have any guess?
The water table limit?
We'll call that exactly. The water table limit has a more proper term. It's called the mean sea level. And so the mean sea level. So this is essentially sea level. So we can see here that actually there are parts of the interior that actually dip below sea level. We'll come back and talk about that here more in depth. And so we're working our way from west to east. And so we got our coast ranges, and then we've got next up the Cascade Mountains. And so you would have drawn the Cascade Mountains. You would have seen the Cascade Mountains eventually come down and essentially form the same thing as the Sierra Nevada Mountains. They're right parallel to each other. And so you can go ahead and pretty much visualize that on the key that I presented to you already. So the Sierra Nevadas, and then in between, we got ourselves a valley. And so this valley is, once again, what's the valley? San Joaquin, also the Central Valley, essentially that valley that you would have mapped, it's right in the middle of California. Once again, one of the most agriculturally productive areas of the United States. Yeah, this is the one that's all well known. The Corn Belt, Great Plains, wheat, corn, all of that. But here's the one that maybe is a little bit less known, the one there in the San Joaquin Valley, in between the Coast Ranges and the Sierra Mountains. Then we have this next area. We call this the Great Basin. The Great Basin, essentially, we're going to come back and describe it, but the Great Basin is essentially a bowl. So it's a bowl. So water, if I pour water into a bowl, where does it go? It goes down to the bottom. And so there aren't any rivers here in the Great Basin that work their way through the Great Basin to an ocean. Everything drains to the middle, to the bottom of the bowl. And we'll come back to that when we talk about the Great Salt Lake. Next up, the biggest mountains in the United States, the Rocky Mountains. The Rocky Mountains are relatively young. And so they are relatively young, although they're kind of like me, would say. Just turned 34, and so they're kind of at that, they're starting to become more of a midlife crisis. So they're almost getting there. So they're not young anymore. They're not like the Himalayan mountains, the youngest mountains in the world that keep on getting taller and taller and taller. They're not as young as these suckers here, but nonetheless, they are quite young compared to the Appalachians. Now we go through a very flat area, and we know this flat area to be the Great Plains. So the Great Plains come off of the Rockies, and the Great Plains come off the Rockies and go right to the interior of North America. And so now we look at the side view, you can see that steady decline. One of the things you notice, though, is as you go west, what happens in the Great Plains?
It goes up.
It goes up. Elevation increases. And so we'll come back and talk about that idea here in a minute. But the Great Plains here actually have an upward elevation as you go further west. So the western cities here that are close to the Rocky Mountains and the Great Plains are at a higher elevation than those further east. Eventually we get to the Canadian Shield or the Central Lowlands. Central Lowlands isn't something we so much mention on a map quiz key, but we know the Central Lowlands as the Midwest. So the Midwest is the Central Lowlands. And so yeah, it might appear that, wow, in southern Indiana, it's pretty hilly. Northern Indiana, it's pretty flat. There's a huge difference there. No, for the most part, we are all part of the Central Lowlands compared to what's going on out west, and to a lesser extent to what's going on in Appalachian Mountains. It's relatively flat here. If you've ventured beyond Central Indiana, you've probably been aware of this. Finally, we get to our good friends, the Appalachian Mountains. The Appalachian Mountains, as we'll talk about here, are very, very old. In fact, they could be the oldest mountains in the world. So these are at the nursing home, they're getting spoon-fed, they're getting last rites, all of that. The Appalachian Mountains are on their way out. They are slowly dying. How do mountains die? We'll come back and explain that. How do mountains die? What are they? They're not living things. We're going to make them living things. Eventually we got the Atlantic Ocean, and so from the Appalachian Mountains, very, very gentle descent till we get to the ocean. Whereas on the other side, very steep. So that's one of the things that makes, in many respects, the Pacific Coast much more scenic, is you can take a drive up the Pacific Coast Highway, for example. You're essentially on a cliff overlooking the Pacific Ocean down below you, which is a much different scene for those of you who've gone to all the spring break places, to Virginia Beach, Daytona, Myrtle Beach, all those various places. It's a very, very gentle descent until you get to the ocean. Alright, so that's the topographic profile going from west to east. Of course, west, as we'll find out, we know the west is much drier than the east, which is much wetter. We'll come back and explain what do I mean by that. So for those of you who haven't figured out what we were just doing, essentially once again we cut a line, or cut right down the middle of North America. We're looking at the side view, and so we've got the various mountains, the valleys, the mountains, the basin, the Rockies, the flat area, and then our Appalachians and the coast. For those of you still trying to get a hold of everything. And so, okay, how can we relate? How can we make this stuff? Because once again, we're TCEM, there we are. There's our TCEM breakdown. So most of us are TCEM. And so I'm guessing you haven't taken a lot of geology classes in TCEM. Of course not. And so I got to try to explain things that are rather complex as simply as possible. And so if you're a hardcore geologist, are you? Anybody? If you're a hardcore geologist, then go ahead. Just rake me over the coals, but do it after lecture. If you want to berate me for how awful this is, that's fine. But I'm trying to make this as simple as possible. And so what we got over here is we got our Mother Earth. And we're going to try to envision Mother Earth just like a hard-boiled egg. And so this is a hard-boiled egg. I know this doesn't look like it, but it's a hard-boiled egg here. And so visualize a hard-boiled egg. It's got that very soft, gooey, plasticky middle, correct? A hard-boiled egg. It's got that soft interior, but it's got a very, very, very thin, brittle outer shell, correct? Very, very thin. So one of the things is we've got this very thin, brittle outer shell of a hard-boiled egg with a very, very soft, gooey inside, just like our mother. Our mother's just the same as a hard-boiled egg. All right, now we got our hard-boiled egg. Things that are hot, do they expand or do they contract? Or do they just chill out and stay the same? They expand. Simple idea. Warm air rises. Warm air rises. We know this. Warm air rises. It goes up. That's why our attics are so stinking hot. But warm air rises and expands. So things that are hot expand outward. Inside our Earth, is it hot? That's the warmest part of our Earth, is the interior. And so essentially, the inside of our mother, not only is it soft and plasticky, it's also extremely hot. And so hot things, they want to expand. And so imagine this plastic in the inside wants to expand. What's it going to happen? What's it going to do to that thin, brittle outer shell? Crack. Boom. 300 level, you guys are tearing it up. Exactly, it's going to crack. Just like imagine an egg, a chicken, getting bigger and starting to crack. Crack the hatch, you know what I'm saying. I'll just move on. Anyway, and so here we've got, essentially now our thin, brittle outer shell has been broken up into pieces. We're going to relate these to plates, tectonic plates. So if you learn about those in K through 12, guess what? They're back again. And so we've got a situation here. Now if I can kind of get you to visualize here. Here we have this line. And this line right here goes right through the middle of these cracks, goes right through these broken shell parts, and goes right through it, and it's separating. And so a very simple idea. Along this line, everything is separating. And so all these individual plates are moving away from the red line. What's going to happen here? They're going to squish each other. And so we're going to get separation here. We get now collision over here. Make sense? And so it's a very simple idea. Where we have separation, on the opposite side of the world, we're probably going to get convergence. We're going to probably get collision. And just imagine if we have a ball here, one side's splitting apart, it's going to then collide with the other part on the other side of that ball. And so thus we get collisions happening. And so this is just like our mother, as we're going to showcase here and relate it to North America. So how does this happen? How do we get separation to occur? And I'm not going to go through too much of this in describing it, but essentially we have these big cracks in the surface. What's coming up through these big cracks is new hot material. Keep in mind, it is super hot under, below our surface, the further down we get. And so what's happening is now we get this hot stuff that wants to come in through these cracks. This very, very hot liquidy material. We think of it as magma, we also might think of it as lava. This very, very hot material. It then comes into contact with water. Or it comes into contact with our air, with the atmosphere. What's going to happen to that material? Is it going to keep heating up, or is it going to cool down? It's going to cool down. And so essentially what happens is this hard material that's liquidy, that's plastically, is going to become hard. It's going to form rock. Let's relate this to our freezer. So if I have a freezer tray, so I have an ice tray, I'm poor, so I just do the ice trays. I don't have an ice maker or anything like that. So I got to pour the water in little cube trays, right? And and I pour the water, and it says, make sure you don't overflow it. Make sure you just put enough water in to fill that little bump. And so what inevitably happens, though, is I put it in my freezer, I take it out, now it all becomes one solid sheet, right? Do you notice that? It all becomes one suspended. Is that true? So essentially what happened was when liquid became, essentially in that case, water became liquid to solid, it essentially expanded. Same idea here. Liquid to solid expands, it gets bigger, and then so what's it going to do over time? It's going to cause separation. As that new rock rises, it's going to condense, it's going to cool, and it's going to cause separation. So that's the main idea. And so another way to imagine it is we got a hammer kind of pushing up this rock. Pushing up this rock that's slowly causing separation to further occur. And you're going to see this play out when we look at North America about 300 million years ago. When we look at it here in a minute. And so here we kind of have to envision, we'll come back to that one. It's a little too early. But here's the kind of something that we got to put and wrap our minds around. Those places that you went to, have you been to Daytona? Have you been to, where else do you go on the, Myrtle, Fort Lauderdale, all those places wouldn't exist if we go back to this time period here. So it's kind of hard to wrap our minds around. Anybody been to Africa? If you were in this time period, if you wanted to go to Africa, you just had to walk right across. You've been boom right there. And so what's happened over time is, there's been a separation that's occurred here. And so once again, the separation I talked about beforehand, and that separation is slowly pushing the United States North America further away from Africa. All right, we'll come back to that idea. And so here, once again, those little individual shelves, those individual plates, we can see those plates here in this tectonic map. I think I got this from Wikipedia, so it's not hard to find. And so what this shows is the individual continents, those individual little bits of eggshell that are on top of that plasticky, gooey, soft interior. And so most of the continents, as we can see here, are riding on top of a plate. One of the things we notice about North America is, for the most part, all of North America is on this one same plate. The only exception are, I guess we could say, our good friend Hawaii and a chunk of California here, which are on the Pacific or a different plate. But for the most part, all of North America is on the exact same plate. We're going to come back to this map here. So how do I make mountains? This is very simple. I'm trying to make this as simple as possible. Two things collide with each other. We just made mountains. Far out, isn't it? And so where we get convergence, and so plate boundaries, oftentimes plate boundaries where we have plates colliding with each other. In the previous example, the blue lines, where we see those blue lines, where we see convergence, where we see plates colliding, we're going to find mountains. And so guess what? On the western side of the United States, the western side of North America, where we have these new mountains being created, we're right there on a plate boundary. So it's kind of simple idea here as far as how do we make mountains. Now let's start off to our good friend, the Canadian Shield. And so the Canadian Shield. What do we need to know about the Canadian Shield, as if this might be an exam question or a fill-in-the-blank thing? All you really need to know about the Canadian Shield is this is the oldest part of North America. So if you think about the surface of North America, this right here is the oldest part. It's been around the longest. And so because it's been around the longest, it's rather flat, it doesn't have much going on, because over time, anything that was there has been eroded and removed away. And so we can tell that things are old by the flatter they are. Things that are young are very sharp, very steep angles. So very sharp, tall mountains are young, where very flat landscapes are seen to be old. And so right here is the oldest part of North America, of the continent of North America. So for the geologists at home, Craton, the Craton. So this is very much the geological foundation of North America. That's all we really need to know about that. We're going to come back and talk about the Canadian Shield and what's going on there here in a minute. But how did the Canadian Shield form? So if we can go back to a few billion years, the Earth was just nothing but hot lava, hot magma, which just that plastically hot going. You could never even imagine walking on this. It was impossible. Over time, though, that material then hardened. So that material that originally hardened, we call it the basement material, the stuff that's been around forever, that's the Canadian Shield. But one of the questions I know you're asking is, well, the Canadian Shield, this looks like it's underwater. What would make the Canadian Shield above water? How is it going to be all of a sudden above water? Two reasons.
Well, does the water drain out?
So water drain out, we can think of as sea level rise, would be one reason. So sea levels have risen and fallen over time. So if you're Al Gore, if you disagree with Al Gore, you can say that, you know what, Al, the seas have been going up and down for a long time, bub. So it's not like it's a new thing. However, Al Gore would say, but it's increasing, the rate of it, rate of sea level change. And so that's one simple reason, one very simple reason. Yeah?
We have continents colliding here, tectonic plates, which would cause rise up.
She said we have tectonic plates which would cause them to rise up. And I'm just going to do this very simply. I wish I had a table. Maybe we can all see it right here. If I got two different things colliding with each other, oh, look at that. We just made a mountain. Look at that. So we got simple. These forces, they're going to be pushing, that are going to cause that land to rise. Very simple idea. And so how is that North American, the oldest part of North America, how is it now above sea level? Was over time convergence and mountain uplift that caused that. And that's just simple forces. Simple forces in which we got this pushing on both sides, which is then going to cause it to rise. Next up, the Appalachians. So the Appalachian Mountains are our next landform to try to figure out. So the Appalachian Mountains, if you don't know now, you know that it goes all the way from Alabama to darn near up here, way up in Canada. And if you can go even further, as we're going to learn here, the Appalachian Mountains actually have its historical legacy way down here, but then all the way to the Scottish Highlands. Have you ever been to the Scottish Highlands? Anybody? I wouldn't go there either. Norway. If you've been in Norway, all the mountains of Norway essentially were created at the same time that the Appalachian Mountains were created. It's all this very same mountain building event, which I'll describe here in a minute. So the Appalachians worked their way across much of the entire eastern part of North America. So they're our good friend, the Appalachian Mountains. And so I'm going to take you back in time, 360 million years ago. And so 360 million years ago, I don't know if you can see this in the back row, but what we've got superimposed here are today's U.S. states. And so you can see Indiana, we can see the Great Lakes, we can see Lake Huron up here. I hope we can see them all. That's kind of why we did the whole map quiz last time, was so that we know what the heck we're looking at when we're looking at these maps here. And so what do we notice about Indiana? Indiana's been underwater for a long time. Much of Indiana's history has been right next to a coastline or underwater. And so the Indiana beach, well, it's actually something that's been around for a long, long time. That's a bad joke, my bad. All right, so Indiana Beach, obviously up here, never mind, that didn't work. Indiana underwater. And so that explains why we've got all that stinking limestone. I'm not going to talk about limestone, how it formed, but it's essentially because we are in a shallow sea, is why we have all that limestone for those of you from south central Indiana. But let's talk more about our Appalachian Mountains here. What's the world supercontinent? Geography K through 12, we learned about the world supercontinent. What it was called? The Pangea, right? We learned about Pangea. This is before Pangea. Pangea, the idea is the world was all one massive continent. That all over time, we saw Pangea earlier when we saw North America right up against Africa spooning each other. We already talked about that. Let's now go before all of that was happening. And so here are what predates the Appalachian Mountains. And so once again, we go up here. This is our good friend, the Canadian Shield. One of the things you notice about the Canadian Shield, it's been here for a long time, and it's also going to be above surface for most of the time as we go from 360 million years to today. All right, so I'm going to try to do, if you recall John Madden, I know he's got a football game that's more popular, but he's a broadcaster. We're going to try to emulate some of the things he would do. All right, so 360 million years ago to 315. And so one of the things you notice about this is what is today going to be the Appalachian Mountains. So kind of focus in on what's happening here. Here's North America, what we call the ancestor of North America. Here's the ancestor of Africa, essentially what is today Africa. And so what we got going on?
Ooh, Clyde, boom, bigger.
Boom, boom, exactly. Does that sound like John Madden? Maybe, I don't know. No one knows what I'm talking about. And so we got two forces coming in, boom! And so right there, 300 million years ago, the Appalachian Mountains have formed. How did the Appalachian Mountains form? Two things coming together, colliding with each other, something's going to give. And so when we have two continents colliding with each other, this is called folding. Not really that important of a term, but folding. So just essentially two land masses colliding with each other created the Appalachian Mountains. The Appalachian Mountains, this is actually, as you can see here, what is today Texas, all the way up to, if we can keep on going, up to the British Isles. And so the steep, the steep slopes there you would find in Scotland, parts of Ireland, are all from the same period here, in which two continents were colliding with each other and banging into each other, creating these landforms. And so when this happened, when the ancestor of North America and the ancestor of Africa came together and collided, now we have Pangea, the term we learn about in K through 12. So Pangea doesn't start until the Appalachian Mountains form. All right, now we're kind of keeping on here. So what we're going to do here? Oh yeah, the Appalachian Mountains. So if you've been to the Appalachian Mountains, they're essentially a bunch of hills. Especially if you've been to Rocky Mountains, they're really very much hills compared to the Rocky Mountains. What happened? Why are these suckers? They used to be just as tall as the Himalayas. Once again, these are one of the oldest mountains in the world. So over time, there have been no more mountain building events. The Appalachians have been done with all of that. So there's no more banging going on for the Appalachian Mountains. Now they're just kind of slowly eroding away as wind, glaciers, rivers slowly remove what once was the mighty Appalachian Mountains. So the Appalachian Mountains are nothing like what they used to be. And so if you could envision the Himalayas, what they look like today, that's what the Appalachians looked like back then. And so kind of a quick 411, this is what I mean by younger. See how these are steeper, sharper, more like what you would see in the Rockies, where these are more mature, let's say. We don't want them to be offended. So these are more mature mountains, more rolling hills compared to the steep slopes that we would find amongst the youth. All right, keeping on. 245 million years ago, let me see, what am I trying to do here? Uh-oh, what we got going on? Let's focus over here on the right-hand side. So right-hand side, what once was Appalachians, or sorry, what once was this collision between North America and Africa, what's happening? It's breaking apart. How is it breaking apart? I showed you earlier. Remember the hammer coming up, heating up, creating separation. So this separation, in my G326 class, I think we calculated at about 21 centimeters per year. So these plates are moving about 21 centimeters per year. So just to kind of give you an idea of how much time, once again, how maybe insignificant we are, is this here, it's looking like we're doing this bam, like as if it's happening in no time. It takes a long, long time for the plates to move. And it varies over time. We're not going to get into that though. So we've got separation occurring. So over time, once again, the Appalachian Mountains have just kind of been hanging out while this separation is occurring. Now let's go over to the other side of the map. So let's take a look over here. What's happening to these guys here?
They're floating away.
No, I was going backwards, sorry, wherever that came from. Boom! Right? Boom! We see this happening here? And so here, this massive plate here is colliding with the North American plate. And so we've got collisions happening over here on the west coast. Boom! And so all that we'll come back to here in a minute. Now let's go back to, let's say about 115 million years ago. What do we have right here in this area? We know it as something else though from our map quiz.
Great Basin. The empty place.
The Great Plains. The Great Plains. And so the Great Plains, if we look at 115 million years ago, the Great Plains-ish. 100 million years ago, the Great Plains-ish. 85 million years ago, the Great Plains-ish. 75 million years. What do you notice about the Great Plains over this 50 million year time frame? It's been underwater the entire time. And so another thing, to quick 411 from geology, is anytime something has been underwater for a long time, it's essentially pretty flat. There's no mountains going to be, there's not going to be a whole lot of construction of landforms in the bottom of a lake, the bottom of a sea. So the ocean floor might be rugged, but when we think about lakes, Lake Michigan's rather smooth. Its bottom, it's this kind of a nice little bowl. So when we think about this here, it's key to understand, well, why is the Great Plains so stinking flat? Well, it had a large amount of time underneath being at the bottom of a shallow sea, so it's essentially being underwater. So that's helping to make it flat. So there's the Great Plains. Now, how in the heck do we have a situation here? Obviously, maybe it might not be the case. The water, it always goes downhill, right? Okay, it always goes downhill. Simple idea. It's called gravity. And so water always goes downhill. And so thus, this here where the water is should be lower than it is there, right? So why is it today the Great Plains, as I showed beforehand, topographical profile, why is the Great Plains higher?
Glaciers, the lake pushing down. I mean, they're rising again now, but
Maybe.
The mountain got bigger.
What mountain?
The Rockies, maybe.
Oh, where are the Rockies at? Wait a minute, because okay, we got a little thing here, or big thing, whatever we want to call it. So we got the Rocky Mountains right through here. The Rocky Mountains look like, okay, here's where Colorado, right? Here's New Mexico. They ain't there, are they?
It's gonna be a boom.
Where are the Rocky Mountains at? 60, 75 million years ago, and we ain't seeing the Rockies. That's what I thought. So what's happening here is the Rocky Mountains are going to soon form. And so essentially we're going to create mountains. And so the Great Plains, visualize, the Great Plains are right here, let's imagine. The Great Plains are right here. Over here we've got collision, the Great Plains are rising. So Great Plains here, this is bad. Great Plains here, central lowland here. We got this convergence happening here, remember, boom. And so we get that boom, that uplift. And so that's why the Great Plains now are at a higher elevation than these areas here, because they've been lifted. So as this plate comes underneath here, it's forcing up, and it's lifting so that this is actually at a higher elevation today than that area there. The glaciers do play a role, and we're going to come back to the glaciers, but we're not going to give them all the credit yet. All right, so here's the Great Plains, Rocky Mountains from our thing I handed out to you. So the Great Plains, roughly this green area, and the brown being the Rocky Mountains. The Rocky Mountains, they do go up further. You could say the Rocky Mountains could go even all the way further up to there, but we'll just let them chill out somewhere there where there's a copious amounts of marijuana up in British Columbia. Anyway, all right, so let's talk about the Rocky Mountains. And so the Rocky Mountains, 65 million years ago, they still ain't here. So 65 million years ago, the Rocky Mountains, I don't see them yet. They're just now starting to form. And then all of a sudden, boom, 60 million. So just in 5 million years, about 10 to 15 million years, let's say, all of a sudden, boom, the Rocky Mountains occur. And the Rocky Mountains form, and they form extremely quickly. So the Rocky Mountains grew very quickly into the very large structures they are today, especially compared to our good friends, the Appalachian Mountains. And so the Rocky Mountains, there they are. But one of the things we note, wait a minute, I thought Andy taught us that all mountains form where?
Plate borders.
Along plate boundaries. And so Andy said that all mountains form along plate boundaries. Here's our plate boundary. We've got the Pacific Plate, once again, remember, boom, colliding with the North American Plate. How in the heck can we get mountain building occurring deep within the continent? This should be occurring here on the coastline. So how in the heck is it occurring in the interior? And I know you don't know, that's fine. Here's how it's happening. So the Pacific Plate's colliding with the North American Plate. And so once again, a very complex animation to help describe how this occurs. And so, boom, colliding with the North American Plate is the Pacific Plate. This is what it's supposed to do. This is what they teach you in geology books as far as what happens when one plate collides with another plate, particularly an ocean plate colliding with a continental plate. What they tell you is that the plate goes down deep underneath the other plate. And so it's kind of a very sharp angle, very steep angle down in that descent underneath the heavier plate, let's say. So the North American Plate. So this collision, this is how it normally is. This is how it is in the Pacific, though. It's kind of going at a more shallow angle. And so now it's going underneath the other plate, but instead of going down deep underneath like that, it's kind of going right underneath. It's kind of a very shallow cut, a very shallow dip underneath the other plate. And so it's a very shallow dip that then comes across, and then there was this, I'm not going to go too much into this, but there's a bunch of rock that then this plate collides with and lifts up, creating the Rocky Mountains. Let's visualize this. Future educators, future K through 12, if you ever have to explain how the Rockies formed, here's what you do. You get a nice big large pizza. So get a nice big large pizza, put it in front of your classroom, get a spatula. And so essentially you got your big large pizza. I want you to come in with the spatula. Try to come underneath the pizza, and once you get about halfway in, lift up the spatula. What's going to happen is you're going to start, in the middle of your pizza, it's going to start to rise up, because that's your spatula poking up, right? And so you got your large pizza, spatula poking up. That's how the Rocky Mountains form. A mountain range that forms deep within a continent, not along a coastline. Does that work? I just made that up, so I don't know. I was going to get a pizza, but 10:30 and I was running late. Anyway, and so that's how the Rocky Mountains form. Essentially a spatula coming underneath the pizza and then kind of just lifting it up. And that lifting it up, you're going to see then a rugged, you're going to see mountain building in the middle of that pizza instead of on the edge. Maybe. That works. I can try that next semester. Okay, I don't think it did.
Next time.
What's that?
Next time.
Next
class. Just bring
We can
us
still get
some-
pizza.
All right. Where are we at? 40 million. Oh, we're almost getting to present. Once we get to present, we get closer to to our halftime break. All right. Where are we going now? All right. So essentially the Pacific Plate, I know I'm going to go back through some other slides that aren't the map, but we know it. It's just continuing to go boom. And so it continues on, and it continues this whole kind of this plate movement. Boom. It's continuing on that way. One of the things that's starting to happen, though, is that we're starting to get separation. We're going to come back to talk about that. But Los Angeles. Is Los Angeles south of San Francisco or north of San Francisco? South. San Francisco is in Northern California. Los Angeles is in Southern California. If you don't know now, you know. However, in about 15 to 20 million years, Los Angeles will be north of San Francisco. Do what? Once again, Los Angeles is on a different plate than the rest of the North American, rest of the continent. And so essentially what's happening is the plates are sliding right by each other. Los Angeles is eventually going to work its way. Los Angeles, give it time, will be up by Alaska. But of course, we'll be all way gone by then, and it'll be a whole lot different scene. But hopefully the Cubs will still not have won a World Series. All right, now let's go back and talk about these last few landform regions. First off, the Great Basin Range. The Great Basin, what we're going to talk about the Great Basin is it's kind of stuck in between two larger mountain ranges. And so it's got the Sierras, or maybe the Cascades, to its west, but then of course the Rockies to its east. And so the Great Basin has two larger mountain chains to its west and to its east. So essentially what it is, it's a bowl. It's a bowl. And so essentially it's just everything drains into the bowl. It's got two higher peaks on both sides, the Rockies and the Sierras. So we're going to come back to it a little bit further, explain the Great Basin. The Great Basin is also where we have very salty soil, very salty sands, and also a lake that's known for being quite salty. And it's not like mean. It's not like a jerk or anything. It's just salty because of its composition, because it has a salty taste to it. Any Mormons in the house? Yeah, we know if you were a Mormon, you know all about that lake. But we're going to come back to it. And then we have next up, keep in mind our Cascades, and we could say this is up here, the Coast Ranges. The Coast Ranges are kind of a combination of the Cascades, but also the Coast Ranges here that kind of continue up. But we won't really talk too much about the ones up there in British Columbia at the moment. But we've got our Sierra Nevadas, and then we've got the Coast Ranges of California along the coast. Here's where you're going to find the redwoods, the sequoias, all the various huge-ass trees. Trees you can drive a car through. I'm serious. You can drive a car through them. They're so big. Then we hit in the middle, have the San Joaquin Valley. And so we're going to try to explain the same Wilking Valley and all these various landforms right now. And so here we have ocean-continental convergence. So here is another way in which we can make mountains. Once again, reason number one we can make mountains is when we have two land things, two just big globs of mass colliding with each other, they're going to create mountains. Another way which we can create mountains is if we have an ocean plate colliding with a continental plate. And so what do you know? We've got that Pacific plate, which I tried to explain, boom, coming into the North American plate. What ends up happening is here. We've got, right through here is where you've got the collision occurring. And so we've got the one plate going underneath the other plate. Keep in mind this material here. This is actual rock of various forms that then is forced down to a deeper level here. And we know the closer we get to Earth's interior, the hotter. And so this material, as it gets closer to this hotter material, it starts to heat up. And so it starts to heat up, and then it heats up, and then creates these landforms, and we know these suckers as volcanoes. And so volcanoes, we also associate volcanoes with converging plates. And so essentially the mountains that are along the coasts that I just explained, the Sierra Nevadas, historically, more recently, the coast ranges where the redwoods were, the big-ass trees I told you about, where those were. Essentially, those are newly formed, recently formed, or in some cases, still forming volcanoes that over time they harden, they die, and when they, of course, when they die, they just don't fade away. They stay there, and they slowly get eroded away. And so these mountain ranges we see along the west coast occur from ocean-continental convergence. And I hope I explained it somewhat easily as far as why does it occur a little bit further away, a little bit more interior, in this case a little bit further to the right of the trench, of the actual collision here. This is the ocean trench, and you can see where the collision happens a little further inland is actually where we have the landform being created. That's because of that whole time it takes to dip and then create the volcanic and the various types of volcanoes that form there. We're not going to go into them too much. And so all of you were born probably after this sucker exploded. Mount St. Helens, I remember it. But I think this sucker almost blew about 04? No. 04 or 05. Very hazy years in my life. But 04, 05, this sucker is about ready to blow again. And it had a lot of attention. Mount St. Helens is a mountain up in, or volcano up in Washington State. It's part of the Cascades. So it kind of showcases the idea that these are still active. These are still being constructed. These are very, very young geologic features compared to our very, very old, elderly Appalachian Mountains. So Mount St. Helens will blow off its top once again, and you'll see it on the news for sure. So the Cascade Mountains, you can see, what do these little triangles indicate? They indicate various peaks. And then we notice, okay, here's where the collision's occurring, but a little bit further inland is where you get those structures here, just like we showed there. Same idea, just applies to the Cascades, and we see the same thing down here. So another quick 411 here. This valley here, just not too long ago, was essentially an inland sea. So as the Sierra Nevadas were created from that subduction, we kind of had a period where it died down a bit. So then it died down, and then we had another one creating these coastal mountains, and so in between, this was a large sea, inland sea, for a good amount of time. Over time, though, it's drained out. That's why it's rather flat. But also, it's kind of, you can see it's parallel to the mountain ranges. All right. Oh, we got one more. Oh, I forgot about our Aleutian Islands, our good friend, the Aleutian Islands. So this is the final one I think I'm going to talk about before we get a break. So the Aleutian Islands. The Aleutian Islands, you should have drawn a circle around these chain of islands coming off of Alaska here. One of the things you note, two arrows coming together means we've got convergence. And so here we've got the Pacific plate colliding with the North American plate, but way up there in the Aleutian Mountains. So what we got going on here, very similar to what I just talked about where we have ocean and continental plates colliding. Here you have an ocean plate colliding with another ocean plate. So if we had to describe the Aleutian Islands, they form from an ocean plate colliding with another ocean plate. And so whenever ocean plates collide with other ocean plates, they create a distinctive feature called the island arc. And so the Aleutian Islands is an island arc It's created from the convergence of an ocean plate with another ocean plate. Couldn't say it any more eloquently than that. So what we got going on here is these chain of islands that form very similar to what I just talked about. One plate gets forced underneath another one. That material, that rock, eventually gets heated up and then creates these volcanic mountains that, if they can breach the water, if they can get higher than the mean sea level, become mountains. So all throughout the middle of the oceans, we've got tons of these arcs, tons of these mountains, but most of them are underwater. And so in the case of the Aleutian Islands, essentially they're mountains. They're just like we talked about the Cascade Mountains. And so the Aleutian Islands are essentially mountains that are called islands just because the tops of them, the summits of them, poke up above the water surface, mean sea level. And so it creates this very distinctive arch here. And so once again, notice the trench, the deepest part, is actually before we get to the land masses. So we've got convergence, the trench is out here, but then the landform, the island arc, is more, in this case, to the left. All right, with that being said, here's the Aleutian Islands. Where is the plate boundary? Which direction are the plates moving? And where is the trench? Who wants to take a stab at these? Where is the plate boundary? Here's the Aleutian Islands. If you can't see them, there they are. If you can't see the yellow line, showcase that. There you are. Where do you think the plate boundary is? You think it's over here? You think it's out here? I think it's somewhere out here. So the plate boundary is somewhere out here. Where's the ocean trench? Same thing. And so the ocean trench is out here. And so we got one plate colliding this way, another plate is pretty much stable up here. So the plate that's colliding this way is actually, the collision's happening out here. But once again, as I showcased here, the island formation is going to be a little bit further interior. And so in that case here, collision happening, the trench you would find here. And so this is one of the deepest parts of the Pacific Ocean. You would think, wait a minute, my bathtub, the deepest part is in the middle of my bathtub. That's not how the ocean is. The ocean is not like a bathtub. In fact, the deepest parts of an ocean are actually going to be along the edges of the bathtub. So that's where we find the deepest trenches there. So there, right there is one of the deepest trenches in the entire world. Yeah, let's take a break. I need a break. Oh, we need to come back to all that. Right on. All right. So let's take a 15-minute break. But something I need you to do sometime during that break is to organize yourselves into 8 groups of 4 students. So I'll let you all figure that out. It's 300 level class. I don't need to spoon feed you on that. So make sure, whatever group you want to be on, essentially all you got to do is just write your names on here. I need all, so you got to figure it out yourselves. And if not, I'll help spoon feed you. Okay, got some makeup. So let's see here. We'll come back at, when it's on the 11, when the big hand's on the 11. So that's 11:55.
Oh,